Hello, I'm at ITU Telecom World in Geneva in Switzerland. I'm talking with Bob Kahn, who is the President and CEO of the Corporation for National Research Initiatives. That's fine, but actually Bob's a very famous man because he was one of the co-developers and co-inventors of the TCP IP protocols, which now run and rule most of the world. He was also responsible for ARPA, the ARPANET, which is the first packetized network system in the world. Bob Kahn, welcome, and thanks very much for talking to us. Can I ask you about what you think about the internet now and in the future?
I think it's a challenge to keep up with the kind of opportunities that will emerge over the course of the next few decades and beyond. Clearly, if the current infrastructure were insufficient to meet what the providers of that infrastructure see as the current needs of the day, they would probably invest more and adjust the rates accordingly so it becomes, a profitable activity for them if they can. Nobody is going to sit and watch their business go out of business for lack of infrastructure. On the other hand, in those places where the infrastructure doesn't now exist, or where we need major investments to create new kinds of infrastructure, I think the challenges are going to be the wherewithal of raising capital in, for example, the developing world, where the infrastructure is much less developed than the developed world, or just finding the business motivation to make the investments in places where there is already significant infrastructure. My guess is that wireless technology is going to be the critical component in the developing country because they don't really have the wherewithal to do all the fixed wireline kinds of implementations, whereas we rely more on wireline stuff for the moment in the developed world, but increasingly that's becoming more and more wireless as well.
And in all this fog and mist of possibility, can you discern a path for the future of the internet itself?
Not if by end result you mean the place we get to where nothing else changes after that. I think there's nothing in the world probably that's got that except maybe a cemetery. Quite frankly, I think the nature of this field is one of constant invention, innovation, evolution. The challenges are figuring out how to support evolution in the system going forward, especially when you've got a few hundred million or a few billion people constantly using it with all kinds of deployed technology. How do you inject new capabilities into that system and have it evolve and propagate? That's partly a technical challenge. It's also a social challenge. It's an economic challenge, and it's an interoperability challenge of sorts to make sure that the old works with the new, if it can, and vice versa. I think that the fundamental issue in the future is going to be coping with serendipity. I mean, there is nobody right now that can give you a prescription for everything that's going to happen. We might say over the next 5 or 10 years with pretty high confidence, we're going to see more broadband deployment. With pretty high confidence, we're going to see more wireless devices, more wireless capability. With pretty high confidence, we're going to see systems out there that allow us to manage information in a more effective way over longer periods of time. And we're certainly going to see more concerns about security and all of the efforts to try and subvert systems that fall within the general rubric of cybersecurity. Beyond that, things are going to show up that none of us have any notion of today. If you think about the last 100 years, who in the 1800s would have predicted, the airplane, television, the laser, transistors, computing? I mean, I'm sure we'll be astounded by what happens even in this 21st century, much less beyond. But I think serendipity is going to be the big driver of innovation going forward.
With all the number of diverse systems that are emerging at the moment and will no doubt continue to emerge, interoperability is going to be massively important. How do we get it?
I think interoperability of different systems is one of the biggest challenges that we have to cope with. I mean, you can talk about interoperability at different levels, like can you move the bits from here to there, which is sort of what the internet and even some of the early networks were designed to do. But at the level of real applications and information systems dealing with each other at the level of what the information is, it's a much bigger challenge. It involves understanding semantics and intent of the data and how it's going to be used and the like. I think that there are architectural approaches which will greatly simplify things, architectural approaches at the infrastructure level in particular. But ultimately, real interoperability is going to be a lifelong challenge, I expect, if we want to get into the lowest levels of semantic granularity that these systems can provide. Why would you want interoperability? Well, if you were a manufacturer or commercial provider of a system, what you want to do is get the biggest usage of that system that you can, so you can develop your sector of the market, most likely. And so you see these individual systems being deployed and used out there. But ultimately, the market starts to saturate. When it saturates, then systems that are even similar want to be able to interact with each other. Data from one needs to be ported to the other. Or, more interestingly, different types of systems get built that need to work with each other. You've got an electronic health record system dealing with digital information, and part of that health information needs to get reported to insurance companies. Insurance companies need to be paid by banks. Some of that has to be reflected in tax returns and reporting requirements. This is a requirement for systems that have historically been built in completely different fashions by different architects and different architecture approaches to now need to interact somehow. And if the requirement for making that happen is special engineering teams trying to figure out how to get system A to work with system B, that becomes a hopeless problem, because you could have a very large number of systems that now have to be specially engineered to work with another very large number of systems. If you had a general approach to interoperability, it would greatly simplify things going forward.
So is what you're saying that we're really searching for a kind of unified field theory for the internet?
I don't know that I'd put it in exactly those terms, but I think what you need is a kind of conceptual approach to interoperability that enables one to understand how their system could work with other systems that were designed by different people in completely different ways. So you're going to need to know when information shows up, what is that information? In what form is it? Can I parse the data structure that just showed up? Can I understand what the terms are? And most likely, you won't want to understand the terms directly unless those terms are also generic. So like, here's a term that you know describes what kind of information follows, but you don't want to embed it in there because that might change so many times in the future. Maybe you can resolve it somewhere else, so that system will then come back and tell you what it is. So it all hangs together somehow at the semantic level as well as the syntactic level.
You mentioned a couple of times one of the buzzwords of nos jours, which is the semantic web. Can you tell us what you think the semantic web means, and also what is the Internet of Things?
Well, I'm not directly involved in the semantic web, but I think what that effort was a way to inject some kind of tagging to allow people to understand what kinds of things they were talking about, so that they could possibly bring a different level of reasoning or discourse to the processing of that information. There's a thing called the World Wide Web Consortium, the W3C, which really took the leadership in that, but I think it was one of the first steps to try and introduce semantics directly. What I was just talking about was introducing the ability to interpret semantics indirectly, which makes it a kind of a meta-level solution to that same problem, which I think could be more broadly implemented. You don't have to buy into just that one way of doing things. You can buy into many different ways, but the same mechanism will explicate it. Now, the Internet of Things is an interesting subject in the sense that some people think of it as different from the Internet, and that the things are somehow going to be talking to each other. In reality, what these networks and the internet is all about is managing information at some level. Managing it to move it, manage it to interpret it, manage it just to access it, or manage it to create it and store it somewhere. So what you're going to be dealing with is not the things, but information about the things. You know, if you consider yourself a thing, I don't mean to insult you, obviously, because you need to identify yourself and you need credentials in order to access sensitive information. It might be your information. It's going to be information about you that you're accessing. Your public keys, coordinates that you might want to share with somebody, maybe biometrics or whatever it is. That's all represented in digital form. If it's the thing is a machine, you may want to know the properties of the machine. If it's a service, you might want to know the properties of the service. If it's a light bulb, you probably want to know maybe what wattage it is, or how you turn it on and off, or what the formats are. So I think the Internet of Things, to me, is just a way of characterizing the kind of resources and components that are in the Internet that you have a chance to interact with.
Now, currently, Dr. Kahn, you are developing the concept of digital object architecture. Can you tell us what that is and why it's important?
Well, first of all, the web is a specific system, and the Internet is sort of a methodology for causing different components to all work together. I think of it as a global information system that defines the routing and the information flows independent of what the components really are. So it's kind of a meta-level prescription for how to glue things together, and it allows for evolution at the component level, applications, services, networks, and the like. The digital object architecture was an attempt on my part to describe a way of managing information that was also at a meta level, so that if you were to create information and decide to trust it to the net, and let's say that you wanted to be able to manage that information now over very long periods of time. This could be the National Archives, it could be government information of all kinds, it could be business information, it could be health records that you wanted to preserve, because while it might be very private during your lifetime, if it can be anonymized or made anonymous, it might provide very useful epidemiology information or studies of how diseases spread. And you might want 1,000 years worth of that data. So you really want to be able to manage this data over very long periods of time in principle. How would you do that? Today, you know, if you look at the half-life of a URL on the web, it's measured probably in a year, maybe a little less, maybe a little more. In 5 years, a very large percentage of them don't work anymore or get 404 errors. If you put something on the digital bookshelf and that had clickables in it, and you wanted somebody to be able to take it off in 100 years or 1,000 years, what do you think the probability is that any of the current mechanisms will still work? The idea that we had there was, if the information is stored in the form of digital objects, which is just data structures that are understood by different machines, not necessarily that you can manifest the data, but that you can understand how it's structured. So you know that this is, you know, encrypted data, and you'd have to go find the key, or this is in this format, and you'd have to be able to manifest the format. Then those data structures can be the essential information if you knew that you could get to it in a persistent way. So the whole idea was to then identify the data structures rather than what we had done historically, which was identify wires on the network, which is how we started. You want to talk to that machine? It's on wire 1. And then you interacted with the machine with your fingers on a keyboard. When those wires started to go to other networks, it wasn't sufficient to say send it to that wire, because you'd have to say where on that next network it should go. We invented the notion of IP addresses. And now the routers could figure out how to route things based on where the eventual machine was. The web introduced the notion of URLs to identify files on particular machines. In 1,000 years, that may all change. But if the identifiers can literally say, this is the data structure I want, then in principle, you ought to be able to get that information in the technology of the day and not be tied to the technology of the past. So those are some of the constraints. So the architecture deals with these objects, identifiers for the objects, Obviously, you'll need to be able to resolve these identifiers to find out maybe where the objects are, or what the terms and conditions for its use might be, and so forth. But you also need places that they can be stored and from which they can be accessed. We call those repositories. The interfaces with those are all identifiers. Interestingly enough, this can be made technology independent because it can use commercial storage technology in the back end. And then the final component of the system are what we call registries, digital object registries, which allow you to register information about the objects, the so-called metadata about the objects, and which you can then use for searching and finding these objects in the future, because nobody's going to want to remember identifiers for thousands, millions, or trillions of different objects, especially if it's their lifetime collections on the net.
Bob Kahn, thank you very, very much indeed.